Morning. Good morning to all of the participants in Indonesia, and also good afternoon to Lydia. Welcome to the guest lecture series today in the course of Synthesis of Organic. So our department and also teaching team here really get grateful that you are willing to join us in the lecture series of Synthesis of Organic Compounds. So as we know that last week is the first week we started the semester, and this week is the second week where we are so thankful that one of the guests have joined us. So today we have Dr. Lydia Scott from Walter and Eliza Hall Institute that will give a lecture entitling Functionalization of Organic Compounds. But first of all, I would like to read Dr. Lydia Scott curriculum vitae. Dr. Lydia Scott is an organic chemist. Her chemical studies involve a combination of both methodological and medicinal chemistry projects toward drug discovery. Dr. Lydia Scott obtained her bachelor degree and honors from the University of Auckland, New Zealand, in the field of medicinal chemistry. In her honors project, she synthesized a natural product, namely indocyanide A and B, under the supervision of Associate Professor Jonathan Sperry. Then she did her PhD studies in chemistry at Monash University, Australia. And in her PhD studies, she developed the first highly enantioselective selective reaction, exploiting a deoxy-Breslau intermediate via NHC catalysis under the supervision of Professor David Lapton. She is currently working in Department of Chemical Biology of Walter and Eliza Hall Institute under the supervision of Dr. Brad Slips. Her work has been published in High Impact Factor journal, such as Angewandte Chemie International Edition and also Journal of Natural Products. I think that's the brief CV of Dr. Lydia Scott. Now we will be listening to her lecture. So to Dr. Lydia Scott, time is yours.
Thank you. All right, let's try and share. Is that all right for everyone?
Yes.
Yes.
We can do this now.
And can you see my my cursor?
Yes, we can see the cursor.
Okay.
Yeah.
Perfect. All right, so my lecture is on the functionalization of organic compounds. So this is kind of an overview of how different functional groups react. So the basis of an organic reaction is between either a base and an acid, or a nucleophile and an electrophile. So in the case of an acid and base interaction, you get proton abstraction by the base, and you form the conjugate base of this acid here. In the case of a nucleophile and electrophile interaction, you have the nucleophile attacking electrophile here with loss of a leaving group, denoted by X. So in order to identify how these organic compounds are going to react, it's important that you're aware of electronegativity. And this is based on the location of these atoms in the periodic table. So just for reference, this is a good resource, and it's really important to note especially these atoms here. So that's carbon, nitrogen, oxygen. You've got your halogens, they'll also be important. Also involved can be sulfur, phosphorus, silicon, and obviously hydrogen. So primarily I'll be talking about reactions that involve nitrogen, oxygen, carbon, hydrogen, and these two halogens. And it's important to note that nitrogen is more electronegative than carbon, oxygen is more electronegative than carbon, same with chlorine and bromine. So that means that electron density prefers to sit on these atoms as opposed to carbon. Carbon relative to hydrogen, these two are quite similar, but they prefer to sit on carbon. All right, so in determining the reactivity of a lot of compounds, it's not only the atom that you're looking at, but the adjacent atoms to those. So in the case of an ester, such as this one here, the carbon is bonded to an oxygen here and an oxygen here. This oxygen, being more electronegative, has a partial negative charge, which leaves the carbon having a partial positive charge. So that means that this carbon and the oxygen, the opposite. It will like to react having electrons. In contrast, you've got a carbon that is partially negatively charged, and that's because it's bound to this magnesium. And that's because the magnesium itself is less electronegative than the carbon. So the carbon preferentially has the electron density. And you can use these rules to apply to different functional groups and just refer back to the electronegativity table if you want to figure out where these carbons are, where these different polarities lie. All right. So the first thing that I'll talk about is the reactions of alkanes, and these are saturated hydrocarbons. So what that means is that these carbons have 4 bonds and they're all sigma bonds. So a primary carbon in terms of alkanes is one that's only bonded to one other carbon. So this carbon here is a primary carbon, and we denote that as being one with a degree sign for primary. Similarly, a secondary carbon, such as the one here, is bonded to 2 carbons. So that's why it's 2 with the degree sign. It's a secondary carbon. And following on from that, a tertiary carbon is one that's bonded to 3 different carbons. So it's not that it's bonded to 3 different atoms other than hydrogen, it's that it's bonded to 3 other carbons. And alkanes are the least chemically reactive of the organic compounds. And that's because the electronegativities of hydrogen and carbon are relatively similar. And also the substitution pattern on the carbon will affect how reactive it is, with primary carbons being the least reactive and tertiary carbons being the most reactive of the alkanes. And that's because the primary carbon has a different dissociation energy of the CH bond compared to the CH bond of a tertiary carbon. And so this is to do with homolysis, which is movement of single electrons. The bond dissociation energy of a methyl is quite a lot higher than ethyl, isopropyl, tert-butyl. So tert-butyl being a tertiary carbon, ethyl being this compound here, and methyl is just a singular CH3. So that means that you're going to preferentially form radicals at a tertiary carbon as opposed to a primary or methyl carbon. So when we're talking about the reactions of alkanes, one of the most important and one of the only is halogenation of different alkanes. So I'm using propane as an example. And one of the questions when it reacts with chlorine is how many chlorine atoms are going to be substituted for hydrogens on the propane. So 1, 2, 3 could be up to 8, as there are 8 hydrogens. And this can actually be controlled by the ratio of chlorine to propane. So propane, if you have more propane relative to chlorine, you're going to get fewer substitutions, so more like 1 or 2 chlorines on a molecule. Whereas if you have more chlorine, you're likely to get more substitutions, so maybe 3 or 4. You also need to determine whereabouts this chlorine is going to add on the molecule. So you've got 3 positions here on the propane. These 2 positions are equivalent. Propane is symmetrical, and they are primary carbons, so they're only bound to one other carbon. This carbon here is a secondary carbon, as it's bound to 2 different carbons. That means that the radical is more likely to be formed here. And so if you're only adding 1 chlorine, you're likely to get addition to the secondary carbon. You're also likely to get a second addition to the secondary carbon. But this reaction isn't particularly specific, so you do actually get a mixture of these 4 compounds, but in different ratios. So the halogenation mechanism follows a radical process, and often it's photoinduced, so that's using light to generate the radical. So it's initiated through homolysis of the Cl-Cl bond, and homolysis is the movement of single electrons. So a single electron from this bond goes onto this chlorine, and a single electron goes onto this chlorine. And electron movement is denoted by a single-headed arrow. So you'll often see double-headed arrows, and that's for movement of 2 electrons, such as a lone pair or both electrons in a bond. So you form 2 radicals of chlorine after you initiate. Following the initiation process, this radical can then abstract a hydrogen through homolysis of this bond here. So you get movement of 1 electron onto the carbon, the secondary carbon here, and movement of 1 electron of the bond to form HCl between these 2. This radical can then abstract a chlorine from another molecule of chlorine, so Cl-Cl. And again, you get the homolysis of this Cl-Cl bond. And that's how you get the installation of this chlorine onto the cyclohexane that I've shown here. And finally, this process can be terminated either through combination of these 2 chlorine radicals, or combination of a chlorine radical and a radical of the cyclohexane. So radicals are also stabilized by nearby functional groups, and this makes them more likely to react at these positions. So radicals can be stabilized by alkenes, and this position here is called the allyl position, as it's adjacent to this alkene. The benzyl position, so that's a carbon bonded to a benzene, that also stabilizes the radical. And this is because you have high electron density in here, and these sorts of groups like to stabilize negative charges. So heteroatom functional groups, they also stabilize radicals at an adjacent position. A ketone radical at the alpha position to the ketone, so that's the carbon next to the carbonyl carbon. A ketone will stabilize a radical. Similarly, a nitrile group or an ether group will stabilize these radicals as well. So I just want to talk a little bit more about these allyl radicals. So your allyl radical can actually sit in two positions. And if we're just talking about the most basic allyl radical, and that's propene, you can form the radical at this position, and the radical can then undergo a shift to this position here through resonance. And that's just electron movement, single electron movement, to move the double bond. So the radical actually exists at both this position and this position here. And that means that it can react at both positions. Just as an example of how a radical reaction works at the allylic position, for instance, NBS can be used to brominate at the allylic position. Normally, a bromine source would brominate at the double bond, but because it's a radical reaction, it brominates at the allylic position. So this is done through initiation with light again, homolysis of this nitrogen bromine bond forms the bromine radical along with the nitrogen radical. And similarly to what I showed before, you get homolysis of this CH bond, and you form a radical here along with Hbr. And this allylic radical, remember, can switch between being located here and being located here. And in the case of cyclohexene, it doesn't really matter where the radical sits because it's a symmetrical molecule. But as I'll show in the next slide, when you have substitution on this ring, then you get a mixture of products. So this radical then reacts with bromine, which is formed from the combination of two of these bromine radicals in a small amount. And you get bromination at the allylic position. So if you have an unsymmetrical alkene, which has an allylic position here, you can form the allyl radical here, but then it can also lie at this position. So what that means is that you'll end up getting bromination at either here or here. You get a mixture of products. So that's about all for the alkenes. They're not particularly reactive molecules, but I'm going to go on and discuss some alkene chemistry now. So just as a bit of revision, the alkene bond is a pi bond and it doesn't undergo rotation. So that means that these groups are fixed in position. You must break this pi bond for rotation to occur. So that means that you can have two conformations if you have an unsymmetrical alkene. And so if you have two groups that are on opposite sides of the double bond, so these two groups are the same and they're on opposite sides of the double bond, that's called a trans alkene. If they're on the same side, that's a cis alkene. And as I've said before, this bond doesn't rotate. So you can't get interchanging of cis and trans unless you break the pi bond. When you have more complex alkenes, you need to use E-Z nomenclature. So E, an E alkene is endgen, which means opposite. And it's shown here how you determine what an E alkene is. Z is Zussman, which means together. So I'll just quickly go through how you determine which one is E and which one is Z. And you need to use the SIP rules. So that's the Kahn-Ingold-Prelog rules. The first rule is that you rank the groups based on molecular weight. So you need to look at either side of the double bond. On this side, you've got these two groups, methyl and hydrogen. So you need to rank these in terms of molecular weight and atomic weight. So a methyl group, you've got a carbon bonded to a carbon. A carbon is higher atomic weight than a hydrogen. So this has high priority this has low priority. In terms of this side of the alkene, you have a bromine and you have a methyl group. So bromine is much higher atomic weight than a carbon. So on this side, your bromine is high priority and your methyl group is low priority. So that means in this alkene, you have two high priority groups on the same side. So you have a Z alkene. In this alkene, you have your high priority group on this side here and your high priority group on this side here. So you have an E alkene. So it becomes a little bit more complex when you have the same atom, but you have varying chain lengths. So in the case of this alkene, you've got a propyl group and you've got an ethyl group. An ethyl group is 2 carbon chain, propyl group is 3 carbon chain. So overall, this has a higher molecular. On this side, you've got a methyl group versus a butyl group. So the butyl group is 4 carbons, methyl group is 1 carbon, low priority, high priority. So you can determine your EZ alkene based on the length of the carbon chain in these examples. It becomes even more complicated when you have double bonds. And so a carbonyl compound is counted as this carbon being bonded to 2 oxygens. Same as if you had an alkene substituent, you would count this carbon as being bonded to 2 other carbons. So that's how you work out your EZ isomerism of alkenes. So in terms of stability, your alkenes are more stable if the 2 bulky substituents are on opposite side. So this is your trans alkene or your E alkene. This is your cis alkene or your Z alkene. And that's due to the steric bulk repulsion. These 2 groups prefer to sit opposite each other so that there's no interaction. Another thing to note about alkenes is that the more substituted alkene is more stable. And the reason for this is a little bit more complex. It's because of hyperconjugation. So when you're talking about this alkene here, you've got substitution on this carbon being the methyl group, and you've also got substitution on this carbon being the methyl group here. When you're talking about a terminal alkene, such as this one here, this carbon doesn't have any substitution, whereas this one does. So this alkene with substitution on both carbons is more stable than this alkene, which only has substitution on 1 carbon. And that's because of the donating effect of the pi bond. So the pi bond can donate its electron density into the CH sigma bond of a substituent on the alkene. In the case of this terminal alkene, you can't get donation from these electrons to a substituent here. So you don't have that stabilizing effect here. You only have it on this carbon. That's why this more substituted alkene is more stable. So in terms of reactivity of alkenes, there's a lot to get through, but one of the most important is halogenation. And this is the addition of hydrogen and a halogen across a double bond. In this case, I've shown hydrogen bromide. And so this undergoes a Markovnikov type addition. And what I mean by that is that it adds to the more substituted carbon. And that's the bromine adding to the more substituted carbon. The hydrogen of the Hbr adds to the more hydrogenated carbon. So this carbon has more hydrogen substitution, this carbon has more carbon substitution. And I'll go through why that is. So following the abstraction of this proton by the double bond, so the electrons of the double bond attack this proton here, the electrons of the Hbr bond move on to the bromine, you get formation of a carbocation. And carbocations are more stable if they have more substitution. So this positive charge preferentially wants to exist on this carbon here because it's stabilized by these methyl groups here. And that's similar to what I was talking about before with the hyperconjugation. These orbitals, this positive charge, can be stabilized by the sigma bonds of these methyl groups. What this means is that the carbocation sits here and then the bromine attacks the carbocation to be substituted at the more substituted position. So this is sort of exemplified in this problem here, where you're trying to figure out where the Hbr is going to add. And it's shown that the Hbr doesn't add to the terminal alkene. So just going over Markovnikov's rule a bit further, the hydrogen attaches to the carbon with fewer substituents. So that's this one. And the X, so the bromine in this case, attaches to the carbon with more substituents. And that's due to the stability of the carbocation. Tertiary being the most stable, methyl being the least stable. But in terms of alkenes, you're only going to be looking at primary, secondary, tertiary. So I've just got a little picture of why that is. And these two species can actually interchange. So because this is more stable, you get a higher concentration of this intermediate, and this is the more likely route through which it proceeds because you have a greater amount of this intermediate. So in terms of this carbocation intermediate with the cyclohexene, this double bond is going to attack the Hbr and pick up a proton at this position, which will form the carbocation at this position, shown here. Bromine can then attack at the more substituted position. Similarly, with this alkene, you have the carbocation at the more substituted position, bromination at the more substituted position. When each substituent is the same, so you have similar substitution at each carbon, these two are quite indistinguishable because they both form secondary carbocations. So this being secondary following addition of this proton, you're actually going to get a mixture of products. So there's no preferential addition of the bromine to either carbon. So why is the more substituted carbocation more stable? And that is due to the hyperconjugation effect that I mentioned previously. When you have a tertiary carbocation, you have this p orbital being stabilized by 3 sigma bonds. Secondary is only stabilized by 2 sigma bonds. Primary is only stabilized by 1 sigma bond. Hence why you get increased stability up in this direction when you get more stabilization by a greater number of sigma bonds. All right, so a more highly substituted carbocation forms faster, and so the reaction will proceed more quickly, and they're more stable than less substituted. This is just an overview of how these carbocations react. All right, so what about when you have this double bond here? It's a terminal double bond. You've got a CH2 here, and this carbon is substituted with only one carbon. But then adjacent to this, there's a carbon that is substituted with two carbons. You actually get a mixture of products where the chlorine from this HCl is added to both this position here and also to this position here. So based on what I've told you before, you would assume that you get hydrogen addition to this position, carbocation formation at this position, and therefore addition of the chlorine at this position. However, what can happen following formation of the initial carbocation is that you get a hydride shift. And so what that means is this hydrogen and its electrons shift to the secondary carbocation. And that's because the tertiary carbocation that then forms is much more stable. So that's why you get a mixture of products, because you get a mixture of these two carbocations. Another interesting thing to note in the reactivity of alkenes is Anti-Markovnikov Edition of Hbr. So this is a bit misleading because it's not actually the Hbr that's causing this non-Markovnikov addition. The non-Markovnikov product being this one here, because you've had bromine added to the least substituted carbon. So what was actually happening in this situation was that you're forming this radical here, this bromine radical, and that's from peroxides in old Hbr. So the peroxide forms this radical here, which can then promote homolysis of the Hbr bond here to form this bromine radical. And the reason that you get substitution at the terminal position is because it's the least hindered. So you get substitution through homolysis of this pi bond, along with along with hydrogen abstraction from Hbr to get the hydrogen on this position here. And that's why you get anti-Markovnikov products as well as Markovnikov products, because you have two competing reactions. The Markovnikov addition of Hbr to this double bond, and also the radical process that promotes the anti-Markovnikov product. So the radical stability I've just put here again, I did mention it previously with the alkenes, but it's similar to carbocation stability in that the tertiary is more stable than secondary, more stable than primary. It's stabilized similarly through hyperconjugation. So an example again of this is the addition to the terminal alkene position, and that's because you're undergoing a radical process. So you get this anti-Markovnikov product here. All right, so when you're talking about adding two bromines, again, this goes through a Markovnikov addition process. But it really only matters in terms of orientation of the molecule as to how this adds. So you're going to get dual addition of two chlorines or two bromines across the double bond. So the mechanism of this is because of transient dipoles between the bromine-bromine bond, and what happens is the electrons of this double bond will attack the bromine and you form a bromide ion. So that's this here. You then form a carbocation, and that will be attacked by the resulting bromide ion, sorry. And that's how you get two bromines added across the double bond. But actually what happens in terms of addition across rigid structures, such as this cyclopentene, is that you get formation of an intermediate that prevents the formation of a cis-added bromine molecule. So, like I said before, you get addition across the double bond and formation of a carbocation. But then you also get transient formation of this brominium ion. And what happens is the partial negative charge of this brominium ion attacks the positive charge of the carbocation, and you get this transient cyclic intermediate. And what happens is that this brominium ion blocks this face of the molecule. So there's facial selectivity of the attack by the second bromide ion. So that attacks preferentially from the top face, and you get this trans-substituted cyclopentane as your product. And you don't get formation of the cis product because you don't get attack of the bromide ion from the bottom face. When you're talking about E and Z alkenes reacting, you get the same product from both E and Z alkenes. That's because you get the same brominium intermediate, so you get the anti-product. Right, sometimes you do get the syn, a mixture of the syn and anti-products, and that's because the brominium ion has restricted rotation. And this is only when you have substituted alkenes. Phenyl, in this case, has an electron withdrawing effect, and it destabilizes the brominium ion, so you get rotation. And that means that you can get different facial attack because you form an intermediate carbocation instead of this more stable brominium ion. Right, another reaction that alkenes can undergo is halohydration. So that's when you get addition of a hydroxy group and also a halogen, in this case bromine. So in order to start this process, you get addition of the double bond to the bromine, you get the formation of the brominium ion, and in terms of being a better nucleophile, water is a better nucleophile than this bromide ion. So you get addition of the water into the opposite face. The water is then protonated, the oxygen is protonated, which then gets abstracted by the bromide ion to form this doubly substituted product. You can also get hydration of a double bond, and that's through addition of an acidic water. So you get formation of the carbocation initially through the attack on hydrogen. You get a carbon-hydrogen bond formed here, and then the more stable carbocation reacts with the nucleophilic water to then form this protonated oxygen, which can then release the hydrogen via the conjugate base of the acid that you've used. And you do get Markovnikov selectivity here because you're forming this carbocation here. You can also get nucleophilic solvents adding. So it's very similar to this hydration mechanism, except instead of this species here reacting, you actually get a different nucleophile. In this case, you've got methanol here, or you can use acetic acid or trifluoroacetic acid. And so you get the substitution in Markovnikov selectivity. So another way that alkenes react is through oxymercuration. a couple of examples are here. And the way that this proceeds is through addition of the double bond onto the slightly delta positive. So that means that this mercury likes to accept the electrons of the double bond, and then you get loss of one of the ligands on the mercury. You form this mercurium ion, which can then undergo attack from your nucleophile, in this case, water. And then you get this process where the hydrogen is abstracted and formation of the hydrated product. And in order to remove the mercury group, you need to reduce it. And then you get your hydrated product. Again, this is through Markovnikov selectivity. And you might be wondering why that is, because you have this mercurium ion here. And that's because you have transient ring opening of the system. So you'll be forming the carbocation at this position, which is the more stable position. This process can also be used to synthesize a number of different functional groups. So I've just shown you the formation of alcohols. You can also form ethers with a different nucleophile, such as isopropanol here. Similarly, you can use a nitrile to form an intermediate imine, which can then be reduced to give your amide. Amines can act as nucleophiles as well, along with amines in an internal sense. So you form a ring system, such as the one here. So a really important reaction that occurs with alkenes is hydroboration. And this actually occurs with anti-Markovnikov selectivity. So that means that you're getting addition of the boron to the less substituted carbon. And the reason for this is due to sterics. And that's because it's a concerted process. So you're getting this sort of semi-cyclic intermediate forming, and these hydrogens create steric bulk. So it's preferentially situated in this position where they're away from this methyl group. So you get boron addition to the less substituted carbon, hydrogen addition to the more substituted carbon. And you have this intermediate formation of a partial cation. And that's at the more stable position as well. And also, because this is a concerted process, you do get anti-selectivity in terms of your resultant molecule, and that's because the hydrogen and the boron add to the same side. So when you're talking about borane, the addition occurs 3 times across this double bond between the borane and the double bond. You get 3 additions of the cyclohexene to the borane. And so there are a number of transformations that can then occur following hydroboration. So often it involves some sort of oxidant. A common one is hydrogen peroxide, and you form the alcohol with anti-selectivity. You can also form ketones, again with an oxidant, such as this chromium oxidant. And along with this, different oxidant can give you a terminal carbonyl, so an aldehyde. Again, you can use an oxidant that has an amine to form amines in the least substituted position. So another way that alkenes react, and there are a lot of them, so they react through carbine addition. And a carbene is a species that has a lone pair. It's highly electron deficient and it's very reactive. So it can be formed, through abstraction of this hydrogen here, this proton by a base. And then if you have a good leaving group, that leaves and you form your carbene here. And these species are highly reactive and will undergo a somewhat cyclic reaction with an alkene, or it can often be a radical process as well. So that's single electron movement. And this is used in the Simmons-Smith reaction. You get addition of this species, which is formed from diiodomethane and this zinc copper compound to get your Simmons-Smith reagent, which then adds across your double bond to form a cyclopropane. And just a few examples of this are shown here. These are all your Simmons-Smith products. And as you'll see, the cyclopropane forms on one side. So you don't get a trans addition of this species. It's from one face only. You can also dihydroxylate your alkenes. Often this is done through osmium tetroxide. And this is a pericyclic process where you form this 5-membered intermediate, and then the osmium gets reduced and the alkene gets oxidized, and you form your dihydroxylated product. Because osmium tetroxide is toxic and expensive, often you use only catalytic amounts and an oxidant to reform the osmium tetroxide. So something like this process here, we've got an oxidant like hydrogen peroxide reforming the osmium tetroxide. And this can then react with another alkene to form your dihydroxylated species. And your diol can then undergo cleavage. Often this is done with sodium peridate. So you get oxidative cleavage of your diol. And this process proceeds through another pericyclic intermediate, 5-membered ring, and you get cleavage of this bond and reduction of your sodium peridate. And there's a few examples of this here. You get formation of these dialdehydes or diketones, or even these diacids when you have another oxidant, such as potassium permanganate. All right, so these dihydroxylation reactions can be stereoselective. If you have two different substituents on your alkene, you might wonder exactly how those two hydroxides are going to add. There's two faces of this alkene that can attack from the top face or the bottom face. So one way to control the stereoselectivity of this is through the sharpless asymmetric dihydroxylation. And this uses these complex alkaloids to control the stereochemistry. So AD mix beta has spatial selectivity from the top, AD mix alpha has spatial selectivity from the bottom. And so you form these two enantiomers. So mechanistically, you have formation of this osmium tetroxide complex with your ligand. So that's the alkaloid. And then this directs the hydroxylation to one face selectively. So a couple of examples of this are shown down here, and you can see you get pretty consistently high enantioselectivities. Another way that these alkenes react is by forming epoxides, and epoxides are these three-membered rings with oxygen. And the way to do this is through oxidation. Often something that's used is MCPBA, and you get addition of this oxygen across the double bond to form this positively charged intermediate, which can then lose a proton and form the epoxide here. Again, there's a few different ways to do this. So you can actually undergo a halohydration first. So as I've shown previously, we get addition of an OH group and a bromine in this case. And then what happens is you have loss of this bromine and attack from the oxygen to form the epoxide. So the mechanism of that is shown here. You get deprotonation of this oxygen, which then forms this alkoxide, which will attack the carbon here to form the epoxide here with loss of this bromide leaving group. Again, with epoxidation, you can do this stereoselectively. And one of the ways to do this is through the sharpless asymmetric epoxidation. And that's just using different enantiomers of diethyl tartrate to control the facial selectivity of the epoxidation. So you get two different stereochemical outcomes when you use this method. And there's a few examples here. Again, you can see these enantioselectivities are all consistently very high. Finally, you can use some different manganese ligands, such as in the Jacobson epoxidation, and that will also give you highly stereoselective epoxidations. And that's based on the ligands on the manganese. So that will control the facial selectivity of the epoxidation. So next I want to talk about alkynes. And alkynes are triple bonded carbons, and they can be doubly substituted. So two different R groups that can be carbons, or they can have one of these being a hydrogen, and that would be a terminal alkyne. So in the case of but-1-ine, this is a terminal alkyne, it's got a hydrogen here. And these undergo similar reactions to the alkenes, except in the case of alkynes, they can undergo two additions in the case of hydrohalogenation or halogenation. And I'll just go through each of these in a little bit more detail. So when we're talking about addition of halides, you've got two weak pi bonds in this alkyne. So the electrons of the pi bond can undergo reaction with this either hydrogen chloride or hydrogen bromide, and you form either the E or Z product, and that's to do with how this forms. This alkene can then undergo another hydrohalogenation to form a geminal dihalide. So the reason that it forms a geminal dihalide is because of the stability of the carbocation it's forming. So what happens is you get addition of the electrons from the alkyne, attacks the proton gets substituted on the less substituted part of the alkyne, and you get a vinyl carbocation, which is more stable at this position than it is at this position. So you get the carbocation formation here and attack of this bromide ion to this position here. And then this process gets repeated again. And that's why you get doubly substituted geminal dihalides. And the reason that this can be either E or Z is because you lose any facial selectivity at this point here. Just with the questions, I'll answer those at the end. All right, so when using bromine, so that's 2Br here, or chlorine, which is ClCl, you only get formation of the trans dihalides, and that's due to facial selectivity. Sorry. And the facial selectivity is due to the formation of, for instance, the brominium ion, which prevents attack from one face. All right, so another way that alkynes can react is through the abstraction of the proton of a terminal alkyne. A terminal alkyne is somewhat acidic, so a base will happily take this proton and form the acetylide anion here. This acetylide anion can then react with an electrophile, so an R group with a good leaving group, such as a halide, and then you get formation of a new carbon-carbon bond here. So there's a few examples down here. You get addition of this acetylide ion to the carbon here, which then loses this chloride ion, which is a good leaving group, to form this carbon-carbon bond here. Similarly with this alkyl bromide. Another reaction of these alkynes is oxymercuration. It's similar to the oxymercuration of alkenes, except following the addition of this OH group, you form an unstable intermediate. So with this process, you get an unstable enol, which can then tautomerize to a ketone. So the ultimate process is this alkane forms a ketone rather than an enol. And so you can see this through this mechanism here, where you get addition of an OH group to this position here, which then undergoes tautomerism to this ketone. Again, with this reaction, you've got an unsymmetrical alkyne. So you do get Markovnikov addition of the OH group. So that means you get hydrogen added to this position and the OH added to this position. And that means that you end up with the methyl ketone instead of perhaps the aldehyde if your OH gets attached to this position. And the reason for this is, again, due to stability of the carbocation. So in the case of just the acidic conditions, you get protonation of the alkyne and formation of this water. The water then acts as a nucleophile and adds the OH2, which can then be deprotonated by another equivalent of water. And that forms this enol here. But as I've said before, the enol isn't particularly stable. So this tautomerizes to the ketone, and that's due to the presence of acid. The acid allows the protonation of the double bond and formation of this new carbocation, which can then be stabilized by the movement of these lone pairs on oxygen into a double bond and deprotonation by another equivalent of water. That's why you get the ketone. In terms of hydroboration, you do get anti-Markovnikov products from hydroboration. So you get initial borylation across the triple bond. In terms of this alkyne, it's symmetrical, so it doesn't matter which end, you get the same product. But what happens is you get addition of borane across, and then following oxidation, you can form the enol again. And like before, you get this enol tautomerizing to the ketone here. In terms of an internal alkyne, which is one that's doubly substituted, you get formation of a ketone, and that's because you have substitution on both carbons. And remember that I said that it is anti-Markovnikov, and that's because you get borylation on the less hindered carbon. So that's the carbon with less substitution. So you get formation of the borane species at this point, and then oxidation to the enol. And this enol will then tautomerize to the aldehyde instead, because you have a hydrogen at this position. Right, and in terms of alkenes being formed from alkynes, you can use a reduction technique to form this alkene here from the alkyne here, and that's through a radical process. You get addition of this radical and movement of one electron from the triple bond to form a negative charge. At this position, this alkyne is symmetrical, so it doesn't matter which way around these are, but then you get formation of a radical at this position and a negative charge here, which can then pick up a proton from your terbutanol. This radical can then gain another electron from your sodium to form a negative charge, and ultimately form the alkene from another protonation event. And if you want to control the selectivity of E and Z alkenes formed from alkynes, you can use different methods. So one method to form an E alkene, sorry, a Z alkene, so that's this one here, where the substituents are on the same side, two hydrogens here. You can use a process using Lindlar's catalyst. And what that means is that you get adsorption of the alkyne onto the catalyst and facially directed addition of H2. So that means that the H2 adds only to one face of the alkyne, forming this Z alkene. When you're using a reductant such as lithium aluminum hydride, you get sequential addition of the hydrogen, and so you get the trans or the E alkene. Right, one moment. Okay, so moving on to benzene. There's a lot of reactivity that happens with benzene, but I'll just try and cover the basics of it. Primarily, it's all focused on the electron density that exists within benzene. So benzene exists as a ring system, and it's aromatic. It has 6 pi electrons, and they exist around the ring in resonance. So although it is drawn as 3 distinct double bonds, the electrons actually exist somewhere around this ring. And you can see that in these two views of the benzene ring. The p orbital overlaps create electron density above and below the ring. And you can see electron density in red through the electrostatic view. And those are the pi electrons sort of congregating. The electron density is also located at the bottom of the ring here. You just can't see it in this picture. So the main reactivity that occurs with benzene or substituted benzenes is electrophilic addition. So that is addition of an electrophile, which I've just shown as E+, onto the aromatic ring with loss of a proton. So in terms of formation of a halide, something like chlorine or bromine is activated by an iron trihalide to form the electrophilic species of either chlorine or bromine. So brominium ion here, and then you can get electrophilic addition onto the aryl group. Another electrophile that can be used is this NO2 group, which is formed from a mixture of sulfuric acid and nitric acid to get this electrophilic species here, which can add on to the aromatic ring. Aromatic groups also undergo Friedel-Crafts reactivity. So what that is the use of a Lewis acid, such as aluminium trichloride, to activate, in this case, an alkyl group, so an alkyl chloride. So this aluminium trichloride is used to generate this electrophilic alkyl species so that it can undergo electrophilic substitution onto the benzene. A similar process is used with an acyl chloride, such as the one here, to form this acylium ion, this electrophilic species here, so that this group can be added onto the benzene to form a ketone, such as this. All right, so the overall mechanism of electrophilic addition is shown here. You get movement of the electrons from the benzene ring, which then dearomatizes the ring, and you form a carbocation here. So this dearomatization process is quite slow because this benzene likes to exist as an aromatic species. So following the addition of the electrophile, you can get a resonance stabilized carbocation. So what that means is that this carbocation likes to exist on certain positions around the ring. And I've shown that in a little bit more detail down here. So following the addition of this electrophile, you would get the carbocation forming here, but this can move to this position here. So relative to the carbon containing the electrophile, in this structure, the positive charge is in the ortho position. In this structure, relative to the carbon containing the electrophile, the positive charge is in the para position. So following addition of the electrophile, the positive charge likes to reside on either the ortho position or the para position. And you can see that it exists in these three forms. So that's why it's illustrated here as being partially positively charged at each of these three positions. And following the formation of this carbocation, it's easily rearomatized by deprotonation at this carbon here. And you get your electrophile onto your aromatic ring. Right, so there's a lot of different ways that the reactivity of benzene can be changed, and different substituents on the benzene are going to have different effects. So in the case of benzene, you can have both inductive effects and resonance effects. And often substituents will have both an inductive effect and a resonance effect. So nitrogen relative to carbon is more electronegative. That means it wants to grab onto those electrons, and the partial negative charge wants to move on to the nitrogen. In the case of a methyl group, this methyl group has a polarizable charge, so it donates electron density into this ring system because of hyperconjugation. But in terms of this aniline here, so that's that nitrogen, you actually have two competing effects. So you've got the inductive effect and you've got the resonance effect. The inductive effect means that electron density wants to reside here. However, the resonance effect means that the lone pair on nitrogen can be donated into the benzene ring. And this is shown in these resonance structures here. So electron donation into the ring can result in having a negative charge at this position instead. So you've got this zwitterionic species, which means that it has both a positive charge and a negative charge. And like with the carbocation that I showed previously, the negative charge likes to sit at the ortho and para positions relative to your substituent. And when we're talking about aniline, so this compound here, the resonance effect far overwhelms the inductive effect. So that means that for aniline, the overall effect is that it's electron donating. So it donates these electrons into the ring. And that's a general rule that inductive effects are generally overpowered by resonance effects. And there's just a little bit of an overview of that here. You can have electron donating groups such as alkyl groups, which are inductively donating, or heteroatoms such as nitrogen or oxygen, which donate lone pairs. Halogens will withdraw inductively because they are more electronegative, but will also donate electron density into the ring because of their lone pairs. And you've got various partially positive groups that can withdraw electron density from the ring. And that's in particular these groups here. Sorry, these groups here. So the partial positive charge of things like a nitro group or a carboxylic acid will withdraw electron density from the ring. And I'll go through that a little bit more in further detail. So aromatic rings can also undergo nucleophilic substitution. So with some sort of leaving group, such as a fluorine atom, chlorine, bromine, you can get loss of this and addition of a nucleophile. And this is promoted by varying your substituents. So this nitro group is electron withdrawing. So what that means is that it can stabilize the resulting products. So what happens is you get nucleophilic addition into this carbon here and loss of this halide here.
So what
Sorry.
conditions are needed so that the major product of Alkene?
Sorry, I can hear someone talking. All right, thanks. Yeah, so you get increasing reactivity based on your substitution pattern. So these two nitro groups increase the withdrawal capacity. And your fluorine is far more electronegative, so it actually is much more reactive because it wants to leave more than these chlorine or bromines. And so the reason why these electron withdrawing groups have such an effect is because they can stabilize the resultant anion from addition of a nucleophile. So because you have negative charge that ends up on the carbon bound to the electron withdrawing group, this is stabilized because it actually jump onto the electron withdrawing group. So that means it's more likely to react. This is through a carbine mechanism. So that's addition of the nucleophile first. You can also get nucleophilic substitution through a deprotonation and leaving of the leaving group. This is much harder procedure, so you need high temperatures, but what happens is you deprotonate and you form a benzene. So it's kind of like a carbine type intermediate, which can then undergo nucleophilic attack and a subsequent protonation event. So you end up with nucleophilic substitution, same as with the carbine mechanism, but this is far more common. Right, so just to elaborate a little bit more on the stability of nucleophilic substitution, when you have electron withdrawing groups in the para or ortho position, you get stabilization of this carbanion ion. And that's because it can reside on the ortho position or on the para position just due to resonance structures. So when it resides on the para position, we've got this nitro group, it's partially positively charged. So it can attract those electrons and stabilize this resonance structure as shown here. When you have the nitro group at the meta position, so that's this position relative to here, you actually don't get any stabilization effect from the nitro group because the carbanion doesn't ever exist on the meta position. And so the negative charge is never delocalized onto this. With the benzene substitution mechanism, we've just shown it up here again. One of the concerns with this is regioselectivity. So in terms of this reaction here, once you form your benzene, you get loss of a proton from here or here, and you form a benzene at this point here. So your triple bond here with loss of this chloride. And what that means is that it can react at both this position and this position. So you get a mixture of products as shown here. So that's all for the benzene reactivity, and I'll just move on and quickly go through a little bit of heterocyclic reactivity. And I'll start with pyridine. So pyridine is a bit unusual. It's got a nitrogen as part of the aromatic ring, and that means that it doesn't quite behave the same as benzene, because often you'll see that this nitrogen interferes with the reactivity. So in terms of a nitration, instead of getting the NO2 group adding as an electrophile, you actually just get protonation of the nitrogen here. And similarly with some kind of Friedel-Crafts acylation, you actually just get blocking of this reactivity because of the lone pair on nitrogen attacking the Lewis acid here. So generally speaking, it's fairly unreactive towards electrophiles. In contrast, it's fairly facile to have a substituted pyridine that undergoes nucleophilic substitution. And that's because of the stabilizing effect of this nitrogen here. Like as I showed you in the reactivity of benzene or its derivatives, you get addition of a nucleophile and formation of a carbanion. which is then stabilized on this nitrogen because of its electronegativity. And so this intermediate is quite stable, which can then promote this reactivity. So following the loss of this chloride, you get your nucleophilic substitution. And this can be done with the loss of chlorine and addition of an amine, and you form your new amine here. Similarly, you can get substitution with a thiol and with base, and that's forming nucleophilic species here through deprotonation of the thiol. Another way that you can enhance the reactivity of pyridine is through the formation of an N oxide. So that's when you oxidize this nitrogen here. And this is often done with a peroxide of some sort. So using a peroxide such as, for instance, hydrogen peroxide, you can form the N oxide here, which somewhat blocks the interference of the nitrogen. So actually it behaves more like a benzene ring. And what you get is similar electrophilic substitution patterns. So you get stability of substitution at both the ortho and para positions when you have an electrophile. So you get addition of the electrophile to the para position in this reaction with a stabilizing effect of the negative charge of the oxygen forming a double bond here, and then the movement of this double bond to this position. And this species here is resonance stabilized. Following the loss of a proton, you then form your substituted pyridine. And in order to get rid of this, this oxygen, all you need to do is use a phosphorus trihalide compound, and that will reduce this species with the formation of the oxidized phosphorus compound. All right, so pyrrole is another heterocycle that's often used in organic reactions, and it behaves a little bit differently to pyridine because it's not entirely aromatic. So it can be resonance stabilized at both the 2 position, which is here, and the 3 position here. So when it undergoes electrophilic substitution, you can get addition of the electrophile here or here based on your resonance structures, because as you can see down here, movement of electrons means that the negative charge can either reside at the 3 position, which is this one here, or it can reside at the 2 position, which is this one here. However, it doesn't actually result in electrophilic substitution at the 3 position, generally speaking. And I'll explain why that is. So just using a Vilsmeier reaction as an example, you get formation of this iminium ion, which is your electrophile. And the favored pathway is so that you get reaction at the 2 position. So what's important to note is that the electrophile adds to the 2 position, and it preferentially does this because you get conjugation, which is in a line. So it's not broken up by this nitrogen. As you can see, the conjugation of these 2 double bonds is in sequence, and this is more favorable. So you get the 2 substituted product. In contrast, the disfavored pathway, again, via this iminium ion, and attack from the 3 position, this conjugated species, but it's cross-conjugated. So cross-conjugated means that it's broken up by this nitrogen. In the case of 2 substitution, we had it in a nice line. and that's far more preferred. And so you get a lower amount of this product formed. You can also get reactivity at the nitrogen because this nitrogen is slightly acidic. So a base is able to deprotonate it. And following deprotonation, you can get formation of an amide with an acid chloride, or alternatively with something like tosyl chloride, you can get the tosylate. Furan and thiophene react fairly similarly to pyrrole, except they don't have this hydrogen here. So there are a few things that they can do that pyrrole can't. So again, the electrophilic substitution preferentially occurs at the 2 position due to the stability of the conjugation when it's not cross-conjugated. So for example, acylation of furan can occur with zinc chloride, and that is just an electrophilic substitution. It can also occur with thiophene, which is the sulfur analog of furan, but at higher temperatures. So the sulfur analog is less reactive than furan. You can also get nitration through formation of the electrophilic nitro group from nitric acid and acetic acid, or you can get bromination. And the bromination preferentially occurs at the 2 position again. However, you can get dibromination, so addition of the bromine here and here, but that can be somewhat controlled by the temperature. So with furan, if you control the temperature to 0, you can primarily form just the monosubstituted. With thiophene, controlling the temperature, you need to go a bit lower in temperature, and you can form the monobrominated species at a lower temperature or the dibrominated species at a higher temperature. You can actually get just full bromination of these compounds, which I've shown here. So that's when it's uncontrolled and you just get electrophilic addition of bromine onto each carbon of the furan or thiophene. In the case of this reaction here, what actually happens is you get the initial formation of the bromine at these 2 carbons, the 2 position, but then you get nucleophilic substitution happening with nucleophilic solvents such as methanol, and you can form this, this species here with loss of your bromine. Finally, with these furans and thiophenes, you can get lithiation. So with a lithium base such as butyl lithium, you can form the lithiated species, and again, preferentially goes at the 2 position, but that's because of coordination with this oxygen. And following the lithiation, this can react with an electrophile. So these are very reactive species. And finally, I just want to talk a little bit about indoles. Indoles have a huge amount of reactivity, but I'm just going to dabble in it for a little bit. Indoles, the reactivity of them is denoted by different numbers on different positions. It's not exactly intuitive. So the 2 position is here, 3, 4, 5, 6, 7, instead of actually just counting around the ring. And preferentially, electrophiles are added to the 3 position. And this is kind of in contrast to the pyrrole, which added at the 2 position. And there is a reason for this. So these electrophiles can be a nitro group, a sulfonic acid group, a halogen, an acyl group, or an alkyl group. And the reason for it adding at the 3 position preferentially is due to the aromaticity of this benzene. So because an indole is a benzene fused heterocycle, it wants to continue being aromatic at this position. When you get reactivity at the 3 position, you can maintain the aromaticity of this benzene. Whereas when you get reactivity at the 2 position, you see that the electrons of this benzene come out of the ring. And so this is a highly disfavored process. And so instead, this process is highly disfavored. Preferentially, you get electrophilic addition at the 3 position. All right, so that's all I have for today.
Thank you, Lydia. It's very nice and very comprehensive lecture, yeah?
That's right.
Very comprehensive because you explain many reactions covering for 4 big organic compounds group, yeah?
Yeah, it was just a basic overview that I was trying to give.
Yeah, it's not only the reaction, but also you describe about the mechanism and also some rationale why some particular product are formed, yeah?
Yeah.
Detail. So now, yeah, it's question time. I found so many questions in the chat box.
Yeah.
Yeah, it's more than almost 40 questions. But I think because of the time limitation, I will just select the question for you.
Okay.
For the next 30
Maybe
minutes.
Burani, you can just allow who want to speak up. There is Dea, maybe first.
Yeah, Dea has raised her hand. Yeah, please, Dea, you can ask directly to Lydia.
Yeah, thank you for the opportunity. Hello, Miss Lydia. My name is Dea. I'm a third years of Department of Chemistry. I want to ask you a question. In halogenation of alkane, you said that the product is there will be formed 2 products of unsymmetrical compound. So what can I do if I just only one of the compound, like there's 2 compound, the product, and I just want one of the compound? Thank you.
So it's actually quite hard to, let me just see if I can get back to there we go. All right, so I think you're maybe talking about this.
Yeah, that's right.
Yeah, so it's pretty hard to control something like this. The only thing that I can maybe think of is trying to block one of these positions with a group that can be removed later. Or often what you'll do is you'll just form both products and then try and separate them following the halogenation.
Okay.
Did that answer your question?
Yeah, thank you.
Okay. Thanks for the question. So yeah, there's no participant who has raised the hand. So I will read several questions from the chat box, yeah, Lydia. Probably one question is coming from Geometry Amal Nur Sheha. Hello, Dr. Lydia Scott. I want to ask you about the initiation process that requiring light. Is there any method to do this process without light? I think it's about the radical process or something.
Yeah, this one here.
Yeah.
So yeah, I've just shown it as light, just as an example. You can use a number of different single electron initiators. So often you can use different photocatalysts. Again, that's with light, or you can use some acids. But yeah, there are a huge range of radical initiators. I've just shown light as being an example of that. But anything that donates a single electron can promote the formation of radicals. or abstracts a single electron.
All right, thanks, Lydia. So another question is coming from Siti Shafira. She's asking about the carbon intermediate, the one that you explained about one of the reactive intermediate. She asked you about why triplet carbine is more stable than singlet carbine.
All right. Well, that's due to the orbitals and the orbital overlap. But yeah, it's quite a complex sort of explanation. And honestly, I don't know it that well. So it's probably good to look up in your textbook, and they'll be able to tell you exactly why that is. But yeah, it's due to orbital overlap and the substituents on your carbene.
I need a lot of explanation, to explain. Another question is coming from Patricia Hendriana. Hello, Dr. Lydia Scott. I would like to ask regarding the oxymercuration process. Does arrangement and there's any arrangement occur in oxymercuration or demercuration?
So are you talking about rearrangement of the carbocation or
the position, or probably, Patricia, can you explain your question more, probably? Hello, Patricia.
Hello.
Yes, Patricia.
I want to ask regarding the rearrangement reaction, that is about the structural isomer.
Okay. So you're wondering if you can form the OH here or here? Is that right? Yeah. So you will form a mixture of products often, and that's because like the difference in stability of a tertiary and secondary carbocation is, while it is different, it's still possible to form a secondary carbocation here. So with this one, you do get transient ring opening of this intermediate to form the carbocation at either here or here. So you might get a mixture of products, but generally you'll get preferential addition to the more stabilized carbocation.
How's Patricia?
Thank you so much. It was very helpful.
Okay.
That's right.
So the next question. Thank you, Dr. Lydia Scott, for the explanation. I want to add other compound.
Go back. All right, so hyperconjugation. What that means is you've got your p orbital on your carbocation. That means is you've got your p orbital, and in terms of carbocation, this is empty, so it kind of wants to accept electron density. And the way that it does that is from these sigma bonds. And it's not entirely clear here because they've got R groups, but these R groups are alkyl chains or methyl groups. So that means they've got CH bonds. And so those CH bonds are oriented like this. You've got electron density here, and that electron density can donate to this vacant orbital here. So what that means is that this is more stable, and the more opportunities there are for this, with more substituents around the carbocation, the more stable it is. So you've got, with a tertiary carbocation, you've got 3 opportunities for this to occur. So that means it's significantly more stable than if you only had two opportunities for this, such as in a secondary carbocation or in a primary carbocation, where you've only got one opportunity for this. Yeah, so does that explain your question?
Yeah. Is it explained? Salma? Does it answer your question? Yeah. I think, yeah, it's explained well. Thank you, Lydia, for that.
Okay.
Yeah, someone's raising hand. Arif Rahman.
Yes.
Yeah, you can
Okay.
ask directly. Yeah.
Hello, Ms. Lydia. I want to ask you about how to learn effectively in organic chemistry. I know that it is hard to learn organic chemistry. So I want to ask you, is it necessary to memorize all reaction, or I just have to know how mechanism works?
So yeah, it's a bit of both. Like the way that I learn it and learnt it was through things like this. So where you understand where electron density lies, how you understand that sterics play a role in where things are going to react, stability. But yeah, I think understanding the general reactivity of molecules is a lot more beneficial than memorizing, because it's a lot more applicable. So once you understand, say, how an ester reacts, you can understand how it might react with different things that you haven't learnt yet. And instead of memorizing, you know, how an ester, you know, gets hydrolyzed or something, you can understand how it undergoes reactions with nucleophiles or gets reduced or things like that, because you know exactly the behavior of these types of molecules. But yeah, I think just basic understanding of electronegativity, basic understanding of acid-base chemistry is really, really important.
Okay, Arif, yeah.
Okay, thank you.
All right.
Basic understanding, yeah, on lots of things. Okay, I think there's a lot of question about Markovnikov and anti-Markovnikov.
Yeah.
One of the question is from Putri Hansa, asking about what are the characteristics of reaction with Markovnikov base or anti-Markovnikov base. Yeah.
All right. So I'm just going to try and find where it is.
Yeah.
Right. Okay. So it's often to do with whether or not a reaction is sequential. And so by that, I mean with something that forms a carbocation, you're getting your initial formation of the carbocation and then the addition of your nucleophile in the case of this halogenation reaction. So if you're doing this sequential formation of the carbocation and then addition of your nucleophile, that's likely to be a Markovnikov addition. Whereas in the case of, say, your hydroboration, such as this, you've got this concerted mechanism. So it's all happening in one step. So you've got the involvement of steric crowding. And that's not seen when you've got the formation of a carbocation, because you've lost any effect of that steric crowding, because even if you initially form the carbocation on this position, it can then jump to the more stable position. So if you've got a concerted process, one that happens in one step, then you're more likely to form the anti-Markovnikov product.
Yeah. Okay, thanks, Lydia.
That's right.
And then another question is coming from Raiza Hanifa asking about alkyne group, one of the reaction from the alkyne group. She asked about hydroboration oxidation. Will this reaction using internal and terminal alkyne reactant produce different product? Why that's the product and how it is formed? And why in the terminal alkyne the BH2 enters at the more unsubstituted carbon?
Yep. Okay, so with the alkyne reactivity, if you're just going through a direct process where you're forming the carbocation, again, it's kind of the same as your Markovnikov and Anti-Markovnikov addition. So with just the acidic process, you're going to form the carbocation at the more substituted position. So it's not going to form here. So like here, if this was a hydrogen, you wouldn't form your carbocation here, you'd form it here. And so that's why you get hydration at this point, and ultimately you'll end up with a ketone. But in order to form the opposite product, you need to go through a concerted mechanism, like with the hydroboration. So this organoborane is formed in a concerted process. So if you go back to, I'm not going to go back to that, but if you think back to when I showed the process of hydroboration, this borane group wants to stay away from the more substituted carbon. So in terms of a terminal alkyne, the borane wants to sit at this position and add at this position, because then the hydrogens on the borane are away from this bulky methyl group. So you get hydroboration by borane adding here, hydrogen adding here, and then following the oxidation step, you lose the borane group here and you get an OH added instead. So that's how you get addition of OH at this position rather than this position when you use a borane intermediate. So it's necessary to use the borane intermediate just because of how the hydroboration occurs.
Yeah. Okay, thanks, Lydia.
That's right.
Yeah, another question is for aromatic group. Yeah, this is from Sultan. Sultan asking about, I would like to ask you about the ortho, para, and meta directors. As we see, ortho and para director can be both activating and deactivating. But why does deactivating meta director do not exist? Thank you.
All right, so,
Oh,
sorry, this is actually supposed to be deactivating.
okay.
All right, I don't know if that confused you maybe, but I'll just go through it anyway. But so the meta directors are always taking away electron density. So they're withdrawing electron density. And in terms of electrophilic substitution, you kind of need that electron density to attack the electrophile. So that's why they're deactivating.
Yeah. All right. Another question about from Adelia. Adelia asked about that she have read a source that saying that geminal disubstituted alkane are more stable than cis or trans disubstituted isomers. Why does it makes that compound is more stable than the cis or trans? Thank you.
Is this in the alkyne section?
I think it's alkene, yeah? Alkene. Oh, alkyne? For the reduction of the alkyne, yeah? Adelia, can you explain more for the question?
Is it this one?
Hello.
Yeah, Adelia,
Hi.
please.
Yeah, I was reading from some journal. They
Mhm.
say the wait, I was forget. The game distributed alkane are more stable than cis or trans this like that. I'm sorry, my English is very bad.
That's all right. You can type it if you want.
Yeah, there was things like that.
It's like geminal, yeah? Geminal.
So like these compounds, the geminal dihalides here.
One,
Yeah, I think so, that.
So are you asking why these preferentially form instead of say the halide on alternate carbons?
Yeah. Something
Yeah.
like yeah.
Okay. Yeah. It's the same sort of answer as the reaction of just a normal alkene. It's because of the substitution and the stabilization of those halogens and the formation of the carbocation. So halogens can stabilize that as well because of substitution. But yeah, it's a bit complex because you obviously do have electronegativities playing into it as well, but generally speaking, it's the more substituted carbocation that forms. And like in order to, and another thing to remember is just that although I have a lot of these drawn as like distinct outcomes, you will see mixtures of compounds when you actually do these reactions. So it's more just a general rule.
Okay, I hope it answered your question, yeah, Delia.
Yeah, that one, sorry, I don't know if that was particularly.
So it's more stable because has 2 electron from alkyl groups.
Yeah, so it's both stabilizing because it's got lone pairs, but then it's destabilizing because you've got it's more electronegative. So it's kind of competing effects. Yeah, which is why it's not a very good answer.
Okay.
Yeah.
I'm understand. Thank you so much.
That's right.
Yeah, we still have a few more minutes, yeah, for the question. Oh, someone's raising hand. Raihan, you can ask directly to Lydia.
Hello.
Hello.
Hello, Dr. Lydia Scott. I want to ask something. I read some of book that explain orthonitrophenol has higher boiling point than paranitrophenol. Why that is happening?
So orthonitrophenol has a higher boiling point?
Yeah, than paranitrophenol. Why is that happening?
Nitrophenol, higher boiling point. It's probably just to do with some sort of stacking interaction between the two compounds. It's hard to know, but so you're talking about, say this was an oxygen, nitro, those two compounds?
Yeah.
The only thing that I can think of is due to some kind of stacking interaction. But also you might get some sort of coordination effects from the nitro and the phenol because you've got hydrogen bonding occurring. So stacking in that sense as well. Generally, when you're talking about boiling points, it's to do with increased hydrogen bonding or van der Waals interactions. So if you've got more prevalent interactions or stronger interactions, then your boiling point's going to be higher.
So how is it, Raihan?
Yeah, I understand. Thank you so much, Miss Lydia.
That's right.
Thank you. Yeah, still have another 5 minutes for the questions
Mhm.
time. There's another question from Dinda. Dinda is asking about why radical reactions are not commonly used in organic synthesis. Why is that?
I don't know that they are uncommonly used. I think people maybe are a bit scared of them, myself included. But yeah, they're definitely becoming more common because you can get different reactivity with radical reactions, and you can get because of things like propagation, you can often get sequential reaction. You get the formation of one product, and then you've still got radicals floating around, so you can get a sequential bond forming step. So yeah, they're definitely becoming more common to use radicals, just because you can get different products from them. They're a bit more selective. In the case of, say, we're talking about allyl radicals, when, just as a basic example, you get reactivity at the allyl position of this compound as opposed to at the alkene position. So that's actually really important. You can select for a position that's commonly seen as a lot less reactive than the alkene. So yeah, I think people are starting to use them a bit more.
Yeah, thanks, Lydia. Probably one more question from Padil Adi Kusumo. He's asking about why does each structure have different bond dissociation energy, and if it binds to another functional group, will the dissociation energy change? Something like that.
Yeah, it will. So I think with this, it's just to do with how strongly that carbon wants to retain the hydrogen, and that is complex. It's sort of stabilized and destabilized by these substitutions. You've got kind of a stabilizing effect when you've got more carbons because of the hyperconjugation. So it's not able to give up that hydrogen when you form the radical. So in these bond dissociation energies, if it's more readily given up, the bond dissociation energies are lower, and if it's less readily given up, then they're higher. And with something like phenol, you're less likely to get the hydrogen given up because it can disrupt the aromaticity. Whereas with something like allyl, you get it's pretty easy to abstract that hydrogen. And you're also talking about functional groups. Yeah, so depending on how the functional group donates electrons or withdraws electrons, that can also affect how easy it is to abstract the hydrogen from these groups. And in the case of something like an electron withdrawing group, it's easier to abstract those hydrogens and form a radical. Yeah, but it does depend on the functional group. Some things are going to make it a lot harder for that hydrogen to be abstracted.
Okay. Yeah, thank you very much for answering all of the questions.
That's right.
Yeah, but I think it's already 30 minutes for the discussion session.
Yeah,
I think
that's right.
You have answered all of the questions very well.
Mm-hmm.
And also thank you to all of the students for all of the questions. Yeah. But
yeah, thank you. It's really good to have so much interaction from you guys.
Yeah.
Yeah.
Yeah, I think it's going to be the end of this lecture. Once again, we are thanks to Lydia for the time, for the great lecture today, and I believe that the student will get a better understanding for some of the reaction, particularly in the functionalization of organic compound. But before that, probably we would like to have a photo session with you. Is it okay? Yeah.
Yeah, that's fine.
Yeah. I hope all of the students can open the camera. Okay. So we have the teaching team here, Dr. Jamaluddin, Dr. Ahmad Zainuddin, Dr. Ika Wiani, Professor Aceh Tatang Hidayat, and Dr. Dadan Sumiarsa as well, yeah, who have joined your lecture today.
Oh, wonderful.
Yeah.
Okay, first page. Okay, I will take the first page first. Okay, 1, 2, 3. Okay, second one, 1, 2, 3. Third one, 1, 2, 3. And the last page, 1, 2, 3. Okay, thank you very much.
Thank you very much to all of the audience and also to Lydia. And yeah, I saw that Dr. Ian Curie also joined us. Yeah, because Dr. Curie will also give a lecture in the next weeks.
Next one.
Yes, you're right. So yeah, once again, thank you, Lydia.
No worries.
Yeah, have a good day.
Thanks for having me.
Yes.
Okay.
We are
Thank
very
you,
grateful to
Lydia.
have
You have a good day.
Yeah, thanks, you too.
Bye-bye.
Bye,
Bye.
Lydia.
Bye.
Mahasiswa jangan lupa isi absen di siat ya.
Ya.
Oke.
Kalau dosen gimana, Pak Diman?
Dosen.
Absen.
Silakan makan siang dulu.
Nggak diisinya di siat.
Oh,
Ya,
bisa di siat.
Siatnya.
Nanti
Isi.
yang berikutnya Pak Jamal ya yang jadi moderator.
Oke, mangga.
Ya, untuk Dr. Ayan Curie berikutnya Billy, Prof Aceh, Pak Jen, Billy Bade, Pak Dadan.
Pak Burani lagi aja, terus
Nama lagi.
Pak Jen mengamati. Maaf Pak Jen sehat?
Oke.
Ya silakan.
Ya udah, mangga mahasiswa kalau misalkan udah absen ya.
Terima kasih ya.
Pak Jamal, maaf,
Ya.
yang di absennya belum ada di siatnya.
Kelas apa?
Kelas C.
Oh, kelas C. Nanti ya, berarti kelas C itu sama siapa ya? Bu Ika ya? Sama Pak Dadan? Bu Ika sama Pak Jen?
Bu Ika.
Oh iya.
Nanti saya siapkan ya.
Nanti
Ya,
disiapkan
Bu.
sama Bu Ika ya.
Makasih, Bu.
Oke.
Pak Dan, kan dosen itu harus ngabsen di siat juga ya?
Absen aja.
Kalau pas bagiannya, ya nanti bisa diklik ya hadir gitu pas di siatnya itu.
Ya, hadir.
Ya.
Suka ngabsen, saya nggak pernah ngabsen Bang Jamal.
Paling nanti ku Pak Yandi di akhir di override, di absenin kalau memang itu teknisnya. Tapi kalau oleh mandiri juga bisa sendiri dosen, gitu.
Nah, kita masih PPKM nggak?
Oh, pengumuman kan hari ini ya, besok perpanjangan enggaknya?
Soalnya
Ini mestinya nanti malam.
Prof Aceh mengajak makan-makan.
tapi kebetulan minggu lalu masih tutup Burani PGG-nya.
Oh iya.
Restorannya masih take away, saya Rabu di sana kemarin.
Oh, belum.
Belum buka.
Asli di luar kalau yang main.
Iya betul.
Ya.
TK juga sudah mulai harus masuk nih di Bandung Bang Pak Jamal. Harus
TK.
Udah, anak Rani juga SD udah masuk.
Iya, udah pada masuk.
Ya, uji coba mungkin tetap buka paling berapa jam dan seminggu berapa hari gitu ya.
Oh gitu.
Tetap izin itu ya, orang tua ya. Kalau uji.
Ya, kalau tidak orang tuanya tidak setuju, tesawi harus lebet.
Iya.
Kok Pak Aceh, ayah TK gitu saha di mana itu TK